Jesse said, my name is Waleed and I've been working on deep learning for the last few years. I switched to it from web development before that, and since then been doing consulting in different areas. But before I continue, I just want to mention that we are doing this event at HackerDojo, and HackerDojo is hosting us for free. So this is a place where you can come and work, and if you're not a member, you might want to consider that. All events, even paid events that are hosted at HackerDojo are free to all members, just so you know. And all right, so I'll talk about convolutional neural networks, and this is going to be a half slides, half code. You don't have to read the code, but I'll explain everything. And I wanted to show you dynamically how this works. So I will start high level and then talk a little bit more technical details. All right, so let's see. Okay, so obviously there's a lot of buzz about deep learning recently, and a lot of it is focused on computer vision, at least the part that I'm interested in. There's different fields. So I wanted to kind of start very high level. So what can we do with it in terms of computer vision? There are a lot of tasks, a lot of things you can do, but the most common ones are these four. Classification is very simple. You give me an image, I tell you if a certain object is in it. I can't tell you where in the picture. I can't tell you how many of this object exists, but I can tell you it's there. So that's classification. Semantic segmentation is like this example shown here. I tell you where the object is and give you an exact mask of it. Like every pixel that belongs to that object gets annotated. But still I can't tell you how many objects there is. I can just say these pixels, the blue one here, the blue ones here, belong to balloons, but I can't tell you how many. Then you have object detection, and this is focusing on how many objects and where they are in the image. So this allows you to throw boxes like individual instances of that. And then instance segmentation merges these two and can tell you where each individual object is and the exact pixels that belong to that object. So what we're going to talk about today is the simplest one, classification. And when I say simple, it's relatively simple because it's still fairly complex when you try to understand how this works. Okay. So the reason it's complex is the computer doesn't see what we see. For us, like you look at the image, it's like so obvious. But when you feed it to a model, you're feeding a big grid of numbers. And imagine this gray area, this scale is removed. It's just a big grid of numbers. It's a big image, let's say 1,000 by 1,000, that's a million numbers. If it's color, RGB, that's actually 3 million numbers. You get those, and a training set tells you this bunch of numbers is a cat, and this bunch of numbers is a dog. Actually figuring out what makes this group of numbers different from this group of numbers is fairly hard. Obviously until recently these things were pretty hard, and they got so much better in the last few years with deep learning. So how does this work? So this is the kind of fundamental building blocks of deep learning. We build a neural network. Imagine the left is the input image. Each circle is a pixel. And then we take the values of these pixels, multiply them by numbers, the W's here, and we come up with a second, we call them a layer, that takes the input pixels, convert them to another representation. So what does this mean? This one, for example, takes an input from every pixel, multiply it by a certain value. Which means if this wanted to only care about this particular pixel, it will have a high weight on this connection and low weight on the others. Same thing for each one. So that's at the fundamental level, this is how deep learning works. You have a relationship that tells you for this particular neuron, that we call it, for this particular neuron, it will activate if it receives input from certain pixels that it cares about. Obviously here there's only 4, but in a typical image, let's say 1,000 by 1,000, there will be 1 million. That can get heavy really quickly. So that's where we go to convolutional neural networks. Instead of having this one layer where each neuron takes input from the 1 million pixels, we make it a little bit smaller. So this is a different visualization of it. Imagine this is the image. This is the layer on top of it. And every cell, every neuron in the second layer reads from a small patch in the image. So in this example, it's 3 by 3. So this neuron reads from these 3, and if we wanted a neuron that activates on only when there's a bright pixel in the corner, then it will have a high weight on this one, low weight on the others, and that's how you get what we call it, a filter. So we have this filter that we run it across the image, 3 by 3, in a sliding window fashion. And then you end up with a second set of results, that one, that identifies certain features. Like you'll find some of them activate if there's a transition from dark to light, another activates from red to green, and so on. And then you build another layer on top of that. So that takes us to the next step, which is now we have a real convolutional neural network. So we have an input image. We feed it through multiple layers, convolutional layers. Each one looks at a small patch and extracts certain patterns from it. The next one looks at the patterns that were generated by the first one and extracts or collects another set of patterns. So what happens here is the first layer can detect only very simple patterns, like 3 by 3 patterns, like an edge, for example. The second layer can detect a couple of edges connected together. The third can connect a couple of edges connected to another couple of edges. And it can detect maybe small circles, or small squares, and so on. And then so on and so on. Each one builds on top of the previous layer, and you end up in the very end with like a face detector, or a car detector, or a cat detector. So, all right. So this architecture is fairly common. It's called VGG 16, I believe, because it has 16 layers. And it was one of the kind of fairly popular architectures early on, a few years ago. Now there are more advanced architectures, but I like to refer to this one because it's fairly simple. You start with a couple of convolutional layers, then you downscale it a little bit, and then you get a few more convolutional layers, you downscale it, and so on. So as you see here, the input is 224 by 3. That's the size of the image. Multiplied by 3 is the RGB. Then you go into 224 by 64. Now we got this kind of like a cube. 64 is the number of neurons per pixel. Then as we keep going, we get to a point where it's 14 by 14 by 512, and so on, until finally 7 by 7 by 512. And then from there, the spatial connections of the image are all gone. It's all 7 by 7. So you've lost all the resolution, all the details, the fine details. But you have a much higher level, kind of semantic level understanding of certain features that tell you what the image contains. And then we pass them through a few more layers to finally make the final decision of, okay, what is in this image. So And I'll show this in code, but this is kind of how it looks. Each layer extracts certain features, and you end up with something that, for example, this one highlights here. But we can try to guess, is that maybe the nose, or the eye, or somewhere there. So that kind of detects what's in that area. So we can try to guess what each filter is doing. We don't really know for sure without actually looking at it. And every time you train a network, it ends up with different settings. Yeah, go ahead.
I have a question. You go back to the convolutional diagram. So when you get down to like 1 by 1 by 496, I'm just having a hard time conceptualizing what useful information you get out of that, because you're like at 1 neuron there, right?
Do you mind repeating the question? Just for everyone here.
So at this level, when we get to 1 by 1 by 4096, the question is what's the information there? The answer is, we don't know. It's a jumble of numbers that get activated based on certain features. So, and this is not a neuron, this is a 4096 neurons. So you can think of it as an image with 1 pixel by 1 pixel, but it's say 4096 deep. And each one of these numbers gets activated, or goes up if there is a particular feature. So one of them will activate if there is a face, one of them will activate if there is a car, one of them will activate if there is no particular pattern that's designed to activate, only if that pattern is missing. And then the combination of those gives us the final guess of what the network guesses, what the input is. Okay. All right, so any questions so far? By the way, feel free to interrupt me if you have any questions. And as I go through the code, feel free to interrupt me or tell me to change the code or do something else or do another experiment. Yeah.
Are we going to go deeper dive into like how we work maybe later on, or like after you do a demo, or maybe should we have those questions?
Sorry, can you repeat that?
So are you going to do a deeper dive into how we work later on, or during the demo, or?
I will explain it through the demo. Yes.
Okay.
Yeah, I will. So just so I know, is this too quick, too slow? Am I giving too little details, too much detail? Who wants more details, more technical?
It seemed like half the people, or
Yeah.
a third of the people were pretty new as well. So.
All right. So I'll keep a balance. Perfect. All right. So in case you haven't used this tool, it's called Jupyter Notebook. It allows you to run code dynamically. So it kind of mixes code and documentation. And I like it because it's pretty easy to explain and kind of demo stuff. So let me just make sure that it's running. So I'm going to restart it. Okay, so the code that I'm going to show is built on Keras. Keras is a library that allows you to build neural networks fairly quickly. And things like that, like building a neural network, like building VGG16, it's actually a lot of work to actually build it, but we've been lucky in the last few years that these are available in neural networks, so now you can do it actually pretty easily with a couple of lines of code. So, let's see. And as I said, you don't have to follow exactly with the code, but I'll focus on the important parts that are relevant. What I skipped on the top is the importing the libraries and writing a few functions that draw images. This is the main part here. So what I'm doing here is using a Keras function called VGG16 and just say, create this network for me. Not only that, but I'm saying, give me a trained network that's already trained. I'm not going to spend a lot of time training the network right now. So this this line of code will do that for me. I think I actually have to run these. I did. All right, so let's do that. The second line says model.summary, just basically print out the. So, in case you don't know about ImageNet, ImageNet is a large data set that contains about 1 million images and 1,000 classes. So people spend a lot of time taking these images of cats and dogs and saying, kind of labeling them, basically. A picture of a dog that says the label on it that says this is a dog. And they provided this publicly, and a lot of people use that to train neural networks. And now we use that as a foundation for a lot of experiments that we build on top of it. So let's see, okay. So I already got a trained neural network. What does it mean, trained? I mean, those W values that I showed earlier, they already have, they're not zeros, they're all high values. So each neuron is kind of already trained to detect certain patterns in the layers before it and so on. Okay, so you see input layer 224, 224 by 3. I don't know why 224 by 224. I'm sure there's a historical reason behind it. For whatever reason, they always train with this particular image resolution. And then you have convolutional layer 2 that belongs to block 1. Then block 1 pool is the rescaling operation. Then block 2, conv 1, conv 2, and so on until you go to the final prediction layer at the very end. Dense means fully connected, which is a network that takes all the input from all the neurons before it, all of them, and gives you one output for, actually it gives you here 1,000 outputs. 1,000 are probabilities for each individual class.
What are the parameters in that last column? What do they signify?
So this is so let's see. Let's say we have a neuron that takes input from 9 pixels. We have to get the values of each W. So we have, since it's 9 pixels, 9 W values, so these are the 9 parameters. So this is the number of parameters for that neuron. And when you have multiple neurons per pixel, each one has that number of images and so on. So this kind of gives you how many float values are in this layer. And the total here is 138 million. So basically, this neural network has 138 million connections between neurons. Each has a particular value, and the knowledge is represented in these numbers.
But how come there are zeros on some of the layers?
These are layers that don't learn anything, like a layer that takes an input and flattens it, or a layer that just scales the input down. Right? So these kind of static, kind of fixed. Okay. So, all right. So you have the network. I downloaded a few images ahead of time. So just to show you what I'm doing, I'm loading an image, and basically tensor summary, I'm just printing the dimensions of the image. I treat the image as a grid. It's a matrix of 224 by 224 by 3. The minimum value is 0, the maximum value 233. Just kind of make sure I got everything is good. And then I'm converting it to floats because neural networks always use float numbers. And then I feed it to the last line, pre-process. So what this does is pre-process the image, which is typically go ahead.
So I would imagine that the ImageNet training would be sensitive to the relative size of the objects within the frame. And I wanted to know whether that was really the case, in your opinion. And then in general, neural networks for images, how sensitive must they necessarily be to relative size of the object?
Sure. So yes. So the question is, are neural networks sensitive to the size of the image? And if so, how much? The answer is yes. Neural networks are sensitive to the size of the image, and they it depends on the training. The way we try to get around that is by feeding during the training. We feed small images, big images. Sometimes we dynamically change the image size to different sizes, rotate it a little bit, change the lighting a little bit. Like we do a lot of image augmentation to make sure the network sees different versions of the same image and be able to kind of figure out. So it's actually pretty important. To us, obviously, you see a cat. It's obviously okay. You know it's a cat. A smaller version of it is still a cat. To a neural network, it's a huge amount of numbers. The smaller version is a very different set of numbers. They don't look anything the same. So for a neural network, it's hard to kind of figure out that okay, something is smaller, it's the same thing. For a neural network, it's not. So that's why we have to kind of feed it different variations to kind of help it figure out which patterns we care about and which patterns we don't care about. Okay, so typically, usually we take the input image, we normalize it, which means we subtract the mean of all the pixel values, so it's kind of fairly consistent, and we feed it to that. So that's what we did here. And then this is the important part, classify the image. I would basically call model.predict, and that will give me, let me remove this. So this is the output. It's 1,000 numbers, and each one tells me how confident the network is in that particular prediction. Each number corresponds to a particular label. So you can see a lot of them are E minus 8, E minus 7. They're really, really small numbers. One of them will probably be closer to 1. And it's going to be very hard to find it. But I'm just going to say argmax, quickly give me that the maximum 1 and maximum 5. I think I'm doing here. Yep. All right. So find the maximum 5 numbers. Map them to. I have a table of like which number maps to which label, and I got these predictions. So Pekingese, golden retriever. So you see, Pekingese is 0.33, like 33% confidence in this class. Golden retriever, 18% confidence, and so on. It's not bad. I'm gonna try it in a different image as well. Same thing, and the same thing, and tiger cat 53%, and tabby 80%. So that's how a neural network works. Takes a whole bunch of numbers, passes them through all these layers, gives you this final output, which is a vector of 1,000 numbers. The highest one is the one that is the classification of that model.
Quick question.
Uh-huh.
For the vector of 1,000 numbers, each number corresponds to an animal or something.
Yeah.
How did they make that mapping, or does it matter? Or?
It doesn't matter. Basically, when you're starting to train, you say, okay, cat is number 1, dog is number 2, car is number 3, and just fix it at that, and that becomes your mapping. So it's fairly arbitrary. Okay. So, all right. So this is cool so far. We confirmed that it's working, and let's see. Now the next step is, how do we dig deeper? This is still a very black box. We know, okay, we can see it works, but what's actually happening here? Now, you asked about the number of parameters, and so was about 180 million parameters. So it's really hard for us to like go look at these numbers and say, okay, what's actually going on? It's really, really hard. It's a lot of numbers, and they're kind of running through layers and layers. It's hard to tell where the inference is happening, what kind of logic the network is following to make this detection. So we're trying to kind of like do, like just like how we try to imagine our brain, how does that work? We can't get into it, so we try to use like other means. So this is basically what we're trying to do. Find indirect ways that allow us to understand how the network works without having to look at each individual number. So a very simple approach. It's like super obvious. Let's take this input image, hide a part of it, make it black or any other color, and run it through the classification and see what the output is, and then move that patch across the image, and then look at the predictions and see how the predictions change. And if we cover part of the image and the confidence in the correct prediction goes down, we know that part of the image is pretty important. So that's what we're going to do here. So a simple loop, I just cover a part of the image with a small box and move it around. In this case, I'm doing, I think 8 by 8 or something, or 4 by 4. So I just move it around, and for each one, I run the prediction, and then I look at the results and see, okay, my top classification class, how did it change? So let's do that. So here, model predict, and instead of feeding it one image, I'm feeding it the whole, I'm calling it heat map X, which is basically a set of images that you see there. So I got a prediction array of shape 16 by 1000. So it's like a matrix, 16 rows, 1000 columns. Each 1000 we know is a piece out that probability of each class. The 16 is the number of images I fed. And let's see. Let me draw that. Okay, so this is the value of the prediction at each of the 16 locations. And you can see that the prediction went down, which is like the black area, when I was hiding those areas. The other parts of the image, when I hide them, the prediction didn't get affected that much. So kind of that tells me where my input is. And to make it clearer, I'm going to apply it on top. So basically, I took these, put it on the image, and I increased the visibility of the image in the areas where the grid matches, and that gives me where the network is actually looking.
So you're calling this heat map, and I'm just kind of questioning the semantics. You're calling it heat maps, but there's also line. Isn't that the same thing? Are you familiar with line?
Line?
Sorry, I forgot the name of it. It's basically a method where you do the same thing. I just kind of wanted to figure out, you know, if everybody's talking about the same thing or different things.
Yeah, maybe. I mean, I'm calling it a heat map. I'm not sure if that's what other people call it. But the idea is I'm trying to kind of look at the image, hide parts of it, and see where the inference confidence goes the lower the most. That tells me this part of the image is more important. So this, if I do instead of 16 boxes, I'll go smaller. I will get a slightly higher accuracy, and but still, kind of, this is like I'm not looking inside the network. I'm just looking at which part of the image the network actually got found to be important, and this kind of is what I see.
Is this the same thing as like the attention mechanism for networks? This is how you determine which areas?
It's not exactly. The question is that, is this the same as the attention mechanisms? Not exactly. It's kind of, I guess, we call it like intuitively as humans, we call it as attention, because the network is paying attention to this. But really, this is the network is looking at everything equally and concluding that these parts are more important for this particular classification. Like the pixels in this area were responsible for the final output we got, which is the cat. Okay, so this is cool. It looks like it's working. Go ahead.
Just in curiosity, the resolution, how does this pixels fit into the image versus false positives? How the equation works? This image is what we see is like a cat versus it's not a cat. Resolution doesn't play a role.
So the question is how does the resolution affect the prediction? And so obviously resolution does affect the prediction and depends on what you train the network. If you train the network on a 100 by 100 image, it will do best on 100 by 100 image. It will not do great on 150 by 150 image. So resolution is important. And through the layers that we kind of mentioned earlier of how like you look at small patches and then you look at patches of patches and then patches of patches of patches and so on. At the end, you get something that's fairly low resolution, but high depth, I would say. And those are the ones we finally look at. And that's why it's kind of like the prediction is coarse, it's not fine. Like this kind of classification network doesn't give you exactly where the cat is. It kind of tell you it's roughly here because we're losing a lot of resolution in that pyramid that we built. There are different tasks that can handle the object detection and exactly finding the exact pixels. These are more complex. But I'd like to keep it kind of simple at this stage for this kind of more introductory.
Just so I understand how this thing works, what's the criteria for determining how much you want to focus on that area? Is it that you're checking for anything within that box that triggers a classification in all of your requests?
Oh, no, it's the opposite. I'm looking at everything else but that box. So this is the input, right? So I feed the first image to the network. If it still thinks it's a cat with like 90% accuracy, I say, okay, so that cat is not that important.
But you're saying, I'm looking for a cat, but I'm just asking, let's say, you don't know you're looking for a cat. Let's say it's, a dog. How does it know that?
Oh, okay, good question. So in this case, we know we're looking for a cat because in the previous step we already kind of detected that this is a cat. Like we ran the inference, the network said, okay, I think it's a cat. So now I'm not questioning that. I'm just saying, okay, you say this is a cat. I want to see which parts of the image make you think it's a cat. So that's my flow. So that's why I'm in this particular case I'm focusing on the class that was already predicted, and I see how it changes when I hide parts of the image. All right, so is it clear so far?
Just one question. What's the impact of the lighting effect?
I answered that earlier, but let me answer again. What's the impact of lighting? When you train your network, if you, for example, you train it on all the images are very clear and good, great lighting, it will work in that condition. But when you give it images that don't have good lighting, it will fail as well. So if you want robust training, you would train it on a variety of images of different quality, different sizes, different lighting conditions. And this allows the network to be a little bit more robust and be able to classify correctly even with random kind of.
So are convolutional neural networks able to do any sort of abstraction? So you mentioned that, science matters, right? But I thought, with convolutional networks, you might be able to extrapolate somehow. As you go higher layers, even though if you show it a smaller image, should it still recognize
value, not as much as we wish it does. So it can manage if it's like slightly smaller, slightly bigger, but not like this. So yeah, you need to provide as much training examples. You need to vary your training examples as much as possible to make it work.
It's a variant to transposition, but it's not a variant to scaling. That's
Yeah.
they're working. Maybe you will tell about something if latest.
Yeah. I mean,
about-
this is definitely an open.
Yeah, but they're trying to make it a variant to scale it as well.
Okay. All right. So let's dig a little bit deeper. So earlier I mentioned the weights of a neuron. So how about we actually take a look at these? So let's see, what am I doing here? So I have model, get layer, block one, conv1, dot, get weights. So in that big image that I showed earlier, you have the first layer. So let's take that very first layer, and which is block one, conv1, and then extract the weights of that layer. So let's do that. Okay, so the shape of the weights matrix is 3 by 3 by 3 by 64. So what does that mean? 3 by 3 is the size of the patch we're looking at in every iteration. The third 3 is the size of the input. So every neuron in this first layer takes input from 3 pixels with 3 colors each, RGB. So that's why 3 by 3 by 3. The last one, 64, is the output size. So now this layer will take this 3 by 3 patch, gives me one neuron which is of depth 64. Well, actually, you can think of it as 64 neurons at that particular location. So it's a little bit, if you run the convolution across the whole image, the input is 224 by 3. The output will be 224 by 224 by 64. So what we did is map those RGB values into 64 values. And this allows the network to say, I detect certain patterns. Like we're kind of transitioning from color space into a different space where we just care about features of the image. And I will show more details as we go through to make it a little bit clearer. So let's display this, please. So here I'm showing the 4i in the range of 64. So these are the 64 filters. So I want to make sure that you can be able to visualize this in your head. The second layer generates 64 neurons for every patch, and these are the weights of those W connections that I showed earlier. In other words, this filter, for example, activates when there is a bright pixel here, dark pixel in dark pixels in this area, and a bright pixel in this area. This is an edge detector, basically. So it detects if there is a transition from bright to dark in this direction. This filter detects blue areas, especially blue areas that happen to have slightly more blue in the center. The interesting thing about this is that when in the early days of computer vision, people kind of intuitively figured, okay, we need to detect edges, and that's how kind of our vision works. And they manually build edge detectors and certain pattern detectors, and then use that to detect things. And here, without telling the neural network anything, we looked at the weights and we realized, oh, it's doing kind of something similar.
So, how do you get blue? You look at the RGB, you look at the B, I guess. You look for a strong weight from B to, I guess that's image number 2.
Exactly. Yeah.
But what if it's negative? What if it's,
So
these weights are positive and negative, so what does that mean? Is it anti-blue? And then you're summing up.
Right. So to make it easy to visualize, we normalize it. So that kind of makes it easier to visualize. But yeah, that's a very good point. A filter could be anti-blue, like have a negative value on the blue pixels and say, okay, this will activate at the absence of blue. So yeah, so totally right. For visualization purposes, we're just normalizing it you can think of it as the gray is the neutral, the zero. Anything below gray is negative, anything above gray is positive. So this actually here, this is saying I want absence of lightness in this area and I want light in this area.
About three channels.
Yes, about 3 channels.
Okay, Waleed.
Yeah.
So another question is regarding the colors in this image. So you said the weights are between 0.7 and let's say minus 0.7, right? And you normalized it,
Right.
Did you normalize it across everything or for 3 by 3?
For each pattern, individual.
For each pattern.
Yes.
And for each pattern, then how do you say, for example, let's say I have this pattern, right? And I have zeros, 0.5 and let's say minus 0.6, 0 and 0.6, right? So how do I get the color out of that, right? Like why is the second one blue all across?
Yeah, so the individual neuron will activate, it's taking input from 3 by 3 by 3. If this neuron is taking its input from all of it from the red channel, that means those waves connected to the red channel are positive, and that displays as red here. And so on. So this trick is easy to do on the first layer, because this first layer is actually detecting colors, and we as humans, we detect colors, so we can understand how this works. This becomes significantly harder if we want to do it at later layers when the input is like 3 by 3 by 64, and the output 3 by 3 by 128, and it's start to become harder. But at least at the first layer, we can do this, and we can clearly see that what the network is looking for in each one of those 64 filters.
I'm wondering if this is a realistic output set of filters, because I noticed that some of these blocks are almost the same. You notice like the blues fields are almost identical. Would that be a realistic scenario?
That is a realistic. This is an actual trained network, which means it might not be super efficient. That shows that there might be efficiencies that we can do. When you train it, you initialize the weights with normal with random weights and let it train.
But after it becomes fully trained, you would expect that it would be all different, right? You wouldn't see any.
No, this is fully trained.
Really?
Yeah. What I'm saying is, there is a randomness to it. This field is still kind of growing and improving, and there's a lot of improvements that we can do. So yeah, there might be duplicate patterns, but it still works, I guess.
So there's still some randomness to how these filters are made.
Yes. And that's the cool thing about it, is that we started with randomness, and we somehow got certain patterns that we ourselves would be looking for if we were to build something like this manually.
Also, I want to make a point. If those are the weights, that doesn't necessarily mean that's the pattern that's going to be ideal for hitting those weights, right? Because weights times themselves, not necessarily.
So, at the first layer, I think this is a very realistic expectation, because if the network is looking for high values for red, and we're displaying it in such a way that if the W's for red are high, we're showing them bright, then pretty much this is what the network is looking for.
So you're saying if there's a patch with that pattern, it's going to respond really strongly to that patch.
Exactly. But it's linear, so it's not going to be like if this patch exists, it's 1, otherwise it's 0. No, it's more like a linear.
I don't know if that's.
I'll show examples that you can actually see this in action. All right, so we talked about the weights. The other important part in the internal of a neural network are the activations. And what that means is we got an input image, we multiply it by these weights, we get values. Those values, we call them the activations. Basically, this is the output of the layer. And then we take those, we multiply them by the weights of the second layer, and we get the activations of the next layer, and so on. So we keep doing that. So the weights are static, because once you train the network, the weights are fixed. The activations are different for each image. Okay, so here I'm just having a couple of helper functions to make it easier to visualize the layer. And okay, so here I'm displaying the activations of the first layer. There's 64 of them. I'm just displaying 8. Why is there 64 of them? Anyone have the answer?
There's 64 filters.
Exactly, yes. So we converted the 3 RGB into 64, so we end up with 64 feature maps. And each one is the result of one of those filters. So let's see if this actually matches. So let's take this one here. You see, it's activating a lot in this area. What's the filter? The filter is blue. What's the image? There's water. So this blue filter is looking for blue areas and activating higher when there's a blue color. Let's pick another one. So here, this is very similar to this. There's a slight difference. This is 0, 1, 2, 3, 4, 5. That's number 5. 0, 1, 2, 3, 4. It's also blue, but the darker blue. So you can see that these filters do correspond with the output of the layers. And one thing to keep in mind here, these filters don't work individually. They work in parallel. So often you will get a combination of filters working on the same patch that tells you this patch happens to be like bluish and has an edge, for example. So we try to kind of simplify it to kind of understand and kind of think of them one at a time. But in reality, they all kind of work together to represent a certain pattern.
Right, so for example, each one of those 64, it could be 3 different filters that add up to each one of those 64. So it could be looking for a lot of blue, but you know, the red in a certain pattern and the RGB, whatever
so it mixes and matches them basically as needed, I guess. Okay. So let's see. Let's visualize the second block. So this is like a couple layers later. And here we have also 64, same resolution. And we're starting to kind of get a little bit blurrier because we're kind of getting further away from the input image. Let's keep going. So this is block 2. And here we lowered the resolution. And now we have 1 is the number of images, 112 is the XY, height and width, 128 is the depth. So we got smaller image, but with 128 channels instead of 64. And you can see that the resolution, like we're losing resolution here. Let's go one more. Now we're 56 by 56 by 256, and we're even using more resolution here. And so on. Let's keep going. 28, 512. 14, 512. 14. What's this? Before we go to this one. Okay, so we got here 14 by 512. At this point, like we lost all the spatial information almost, and we're looking at one of at each location, one of 512 values that tell us something about there that the network has found. So here what I'm trying to do is, let me pick one of these. So let's pick number 0. So what I'm doing here is apply a mask of that first image, kind of overlay it over the actual picture to see what pattern is activating that thing in the corner. It's hard to tell. It's something in the corner of the image. So for whatever reason, that particular pattern activated these particular signs. Let's look at 1, 2, 3, 4. This is like transition from blue to kind of brownish area. So as you can see, it's what we think of patterns, like a face or a plane or a circle. The neural network does not necessarily share our understanding of what's a pattern. It mixes and matches them in a different way. So the way it works is it's not always intuitive to us. We can try to guess, and like we can look at, let's say this one, 0, 1, 2, 3, 4, 5, 6, 7. 7 because it's like a pixel there. See, it's not very clear why that particular neuron is activating on that area. It's clearly looking for that pattern, but most likely this is working with another filter at the same time. They're all working together to activate and kind of detect a certain pattern. If we keep searching, we will probably find a neuron that activates when there is a nose, there's a face, and then we can say, okay, this is the nose neuron. Okay, we found it. You have to search. Go ahead.
So when you apply the mask, so you just extract the fifth layers, weights, and see where's the value, the pixel value, have larger value.
No, I believe I'm taking the activations, not the weights,
Okay.
and using them as a mask. So it's a simple overlay. It's just taking this one, overlaying on this, just so that visually it's easy to see, okay, where this corresponds in there.
But the receptor field in the console 5 is larger.
Right. So yeah, good point. I guess if I change apply mask to, yeah, that's actually a pretty good point. Okay, I'm not gonna do that right now. But to repeat what James said, at a higher level, we are in block 5, which is basically already like we passed about 10 or so layers. When we see this neuron activating, it's looking at the 3 pixels before it, and each one looking at the 3 before it. So this is actually getting its result from a pyramid. So it activates on a larger area than what it looks. So it's actually like, it's probably looking at something around like this much or something like that or more. And basically saying, okay, I found a particular pattern. So that's why when you visualize it this way, it might not be very clear. Okay, so how about the final layer? So we kind of progressively took edges and mixed them and kind of mixed things until we got to some kind of hierarchical patterns. At the very end, that's when we need to make a decision and say, okay, now we have to decide the class. So far we haven't, we just kind of picked the patterns. The last layer, which we usually it's a fully connected layer, takes the values of these features from everywhere and multiply them by weights again, so you can see it's a very repetitive type of architecture, and gives you the final 1,000 values. Now, because these are 1,000 one-dimensional, I'm plotting it as a histogram, as a graph rather than an image. So class 200 something is clearly much higher. A few classes next to it are low, and everything else is 0. That's a typical classification output where you see one class, the network has fairly high confidence in it, and everything else is very close to 0. Any questions so far? Cool. All right, so we use the patch approach to see where the image areas are important. We visualize the weights, we visualize the activations. Another thing we can do is reverse how the network works. What if we start from a neuron or a class and say, okay, can we work backwards and see what we get on the inputs? Like, can we make a particular class here, just like we started, we force it to be a high value, then look before and see, okay, what do we need to put in this layer to get this to be a high value? And then we work our way backwards. And that will allow us to look at, like, it's another way to look at how the network works and try to figure out how to do it. So there are many ways to do that. One way is to treat the input image as a random value and try to apply training, just like we do the typical training. In the typical training, we have input, we have a label, and we do a training to set the values of the weights. This will fix the label, fix the weight, and we run training to predict the image. So, similar approach, just like it's an equation, you're changing which variable you're trying to calculate. And in this case, we're thinking of the whole network as a function, an input, a function, an output, and we're trying to, we have the output, we have the function, we're trying to predict labels.
Oh, it's a big function.
Alright. So I'm not going to go through the details other than what I mentioned. So typically when we train, we need a loss function that we want to optimize. And in this case, I'm going to say I want to optimize that same label, the cat label. And I want to optimize that. Basically, change the input until I get something that optimizes that value.
Okay, I will ask.
Okay.
Aren't there several possible answers? Right? Just because.
There are many,
Yeah.
many, yes.
So you're not guaranteed that that's the the local mean.
That's correct.
All of that. It's a answer that answers the question.
Right. Yeah, definitely. So, and we'll see. And the results might not necessarily be what we want. It's gonna be something
That's how
different.
they generate deceiving images, to deceive the net.
Yeah.
Yeah, but you still don't know exactly what the network is looking for. You just know that this kind of triggers it, and whether it's the only one.
Yes, for sure it's not the only one, but we can still, like I guess with the examples, will kind of make that clearer. Yeah, good point. All right, so a quick note about backpropagation, because if you're going to talk about neural networks, you might as well know what backpropagation is. So, so we have an input, we have a network that's untrained, and we have the output that we know. A picture of a cat, a label of a cat. A picture of a dog, and a label that says dog. We want to solve that equation and kind of figure out the values for the weights. The way we do that is, if you think of it as a simple function, it's not simple, but the same principles apply. If it was a simple function, then we have the input, we have the output. We calculate the gradient of that function. So if it's like a one-dimensional function, it's obviously calculate the gradient of that. You say, okay, I just need to kind of walk in the direction of the gradient. So I have my loss function, and the gradient at each point tells me how the curve, what the angle of the curve. And I just change my input until I get to the lowest value. And pretty much that's how, at a very high level, that's how we compute it. And it's called back propagation because I start from the end and say, okay, this is the label that I want. What change do I need to make to these weights to give me that? And then what change do I need to make to the weights before this to give me the output, the last layer needs to see, and so on. So I calculate, basically we call it the gradient, and we multiply that by a certain number of value, and basically it allows us to gradually move into a solution. So we're going to do the same thing here. And what you see here is the gradients of the image. So it's probably a little bit hard to explain through how that works internally. Think about that. But the bright values here are areas where the gradient is high, meaning a change in the pixels in that area will have a large effect on the output. So changes in these areas, the gray, are low. And remember, this is a normalized image, so gray is 0, white is positive, black is negative. So the gray areas are places where if the pixels change, the output will not change that much. The bright areas are areas where if the pixels change, it will increase the confidence in this prediction. And the black areas are, actually the black and the white, they both kind of work together. These are the areas where the gradient is high, meaning changes in the inputs causes a big influence on the output. So another way to kind of visualize how this is working is basically to see, look at this and say, okay, it's clearly looking at this. These areas are influencing the prediction that we got more than the edges and the bottoms of the area there. So, yeah.
Question. I'm wondering, you notice that most of that light area there corresponds like the dark areas of the picture. So I'm just curious, how does that work? I mean, I would expect, the lighter areas on the right side, where you can clearly see the cat,
Yes.
would activate better than that whole dark area.
Right. So, depending on how you train it, so neural networks are really good, give you really good results, but they might not do it in the same way we think. It's might be looking at different patterns. It totally could be the wrong patterns. One good example that in one of Google's papers was about trying to detect a dumbbell to see what the network is looking when it's looking for a dumbbell. And it turns out it was looking for this part of the arm. Because it happens in the training, because there's always someone holding a dumbbell and there's always this arm. So the arm was a big part of predicting a dumbbell. So I don't have a good explanation for why it's kind of looking at this, except the fact that just because it's located there, it does not necessarily mean it's like looking at this exact pixel. Each one is looking at a fairly large patch, because this is we're looking at the whole network. So
Right, and that's because it's discriminant training, right? It's trained on 1,000 objects to detect differences between them.
Yeah.
If there are many objects that are different in one feature, it will notice only this one feature. That's all. It will not notice anything else around.
right.
Right.
Yes, exactly. So another example that I sometimes mention is when if you're training on a lot of images, and let's say you collected pictures from different photographers, and one of your, the photographer that got you all the tiger images happened to have a dead pixel in his camera somewhere, and the model might decide that, okay, all these tigers, always there's a certain pixel that's always dark in this area, and might conclude that that's what defines a tiger. And it will be correct, technically. It's not necessarily the pattern that we expect. So that's why visualizing these data is actually useful. Sometimes we get surprised by how the network reads that.
One way that makes sense to me is that this is not the most ideal picture of a cat, and it may actually look more like a cat if we had changed some pixels to make it look like there was more light on the left side of the face.
It's possible. It's possible, and it's possible also that for whatever reason that particular shape happens to be important. Unless you actually go look at the training images and compare, you might not know. Yes.
I think explanation is very simple. Why both left and side of this images are equally important? It's very simple because you see it's dark, but in fact there are patterns there. And they're equally important on the left and on the right. That only means that your network was correct.
What you're saying is that the
The dark
patterns.
area also contains features, and flat area contains features. They're equally important.
Yeah, that's a good point. That's a good point. It's basically, I guess, to repeat the explanation is, it's possible that we see it black, but it's actually not black. When you look at the details, it's actually, there is certain patterns, and that whatever patterns the network needs are there.
Well, my point was, even if it was below the threshold that was completely black, saturated black, it would still be important because it may look more like a cat as it became brighter, even though this particular image isn't brighter. But yeah, that's a good point that there are maybe some details that we're not seeing. Because it's just fairly
If you normalize the image, you might see. And they're equally important in dark and in white. And that's correct.
But they're equally important whether or not they're present in this particular area. That's how it seems to make sense to me.
But it would be interesting to see how just to change the contrast of that image as verify it's not actually there.
It's just making sure that the black area doesn't have any other features which can resemble another animal. So that may be a dark, maybe get considered as a shadow versus if other features comes and then.
So that's another explanation. See, that's a good one also, because usually pictures have shadows, and shadows tend to be there.
But this image, the left image, is a characteristic of the image on the right. It's not necessarily a characteristic of the network, right? It is combination of both.
Yes.
So the network may expect all these features of the cat in different places of the image. It is just for this particular image, it looks for those characteristics in those places, right? So
Yes.
so that's why it's oriented the same way that the cat is oriented, right?
Let's run a different image and see how that works.
So just a quick time check, you're a
Yeah.
little over an hour.
So how much time do we have?
I don't know, maybe another 5-10 minutes.
Oh, okay. All right, then I guess I'll skip that part.
You can obviously go, if you want to stay after, and if you're game Waleed, you can
Sure.
get a smaller group as well.
Okay. So, all right. So these are currently the gradients, and the next step, what I'm going to do is use these gradients to generate an image. So this is to try to actually generate an image that should satisfy these classes, this classification. So the way I do it is generate a random image, and then I do a loop here. I'm doing 50 iterations. Basically, this is almost identical to how you train a network, except in this case, I fixed the weights of the networks, and I made the input image a variable.
Isn't that similar to the other one that you just varied the input, the input image, but just now your initial condition is a noisy image as
Yes.
opposed to previously it was
So
picture.
this one, these are the gradients. These are the gradients of the input as opposed to the actual values.
But you still start, I mean, you're still doing the gradient.
Here I'm not doing the gradient. I'm just calculating the gradient of the image relative to
The output. But you're still doing the same thing there, because a class is an output, it's just you're starting with a random image.
It's a subtle difference. So this is the gradient. The next step is using this gradient to see, okay, can I change the pixel values in the direction of this gradient?
So he hasn't applied the gradient yet.
Yes.
He's
So,
gonna apply the gradient.
okay. So this is the result of applying the gradient. So
Okay, so he's doing the gradient on the random pixel?
on the random pixels. So apply the gradient on the random image, go through 50 iterations until we get an input. And according to our network, this is a perfect image of a cat.
Meaning, what's the confidence?
That's exactly what I do next. So I'm going to classify that image and tiger cat with the accuracy of 95%.
Wow. Wow.
That's really,
So
Looks like, I mean,
that's close enough.
yeah.
So this is another way to look at, okay, how is the network actually working? It's not looking at the same things we're looking at. It's clearly, the most important things to it are certain patterns in the cat. That's like, if you look, it kind of looks like a face. I mean, you can, if you kind of squint a little bit, kind of looks like a maybe. So, and if I run it again, I will get something different, but probably not very different. So, like when people talk about adversarial examples and how it's so easy to fool a neural network, that's why it's out of the all possible types of input images, we're feeding it a very, very small subset. Like a million picture is a lot, but it's a very small subset of what possible pictures could be. And the network is looking at certain things that keep happening, and that's what you get. So, kind of this is one of the weaknesses of neural networks. It's so easy to fool by if you understand what it's looking for. Okay, so what I did here, we're almost done. I took the final class, the final prediction, walked through the layers backward, and tried to predict, to generate the input. But I don't have to start from all the way at the end and say, okay, give me a cat. I can start from somewhere in the middle and say, okay, this neuron, what input will activate this particular neuron most, and that will give me also another insight into how the network works, like what kind of patterns it's looking for.
So did you take this image and put it as an input and see?
Yes, I just did here. Sorry, I did it very quickly. Yeah, I fed it as an input, and I got 95% accuracy, that is a tiger cat, 1% accuracy, that is a tabby, and then 9 Egyptian cat. Alright, so the final thing here for tonight is this code block is similar to the previous one, except instead of optimizing for the very last label and say give me something that optimizes for the cat, I'm optimizing for some random. So I'm choosing here block 4, column 2, the third neuron, and say, okay, optimize for this. Okay, so this neuron activates on this kind of pattern. Let's randomly pick something else. This neuron detects this kind of pattern. If we go, so block 4, let's go to block 2. Kind of earlier in the, closer to the image, we will get simpler patterns. Let's go to block 1. Very simple pattern. You can see a little bit, it's not very clear here, but there's a little bit of kind of gray spots. Yeah, so I guess block one is give us very, very simple patterns, but go higher and we get more interesting patterns. And yeah, you can play with that and figure out, okay, you can kind of figure out which neuron gets activated by what kind of patterns. And you can see these patterns are fairly kind of complicated, like circles and lines in different colors. So at higher layers, activating these neurons only happens with fairly complex shapes. And that's when you combine these together in a certain way, you can detect. Okay, so I guess you mentioned the object detection thing. I'm just going to kind of mention that very quickly. And so this is one of the this is a little bit harder, more complex than classification. This tries to find the objects and their masks, and this is available on GitHub. I built that as part of my work with Nanoport, and then we open sourced it. And so a lot of people are using it, and it allows you to do object instance segmentation. And we have a lot of people took this model and built on top of it a lot of pretty interesting examples, like applying it on 4K video and applying it to, it's not very clear in the here, but this is an aerial image, and it's trained to classify sports fields. This is another example that changes all the image to grayscale except balloons. Another example that is used to segment nuclei in microscope images, and detecting surgical robot instruments.
And is being done real time?
No, these are recorded. Detecting houses. So yeah, so this is another maybe a topic for another day if you are interested in instance segmentation. And yeah, thank you so much.
Thank you, Waleed. All right, just a couple of quick closing remarks. Again, thank you, Waleed, for giving us this presentation. Had awesome audience participation, a lot of good engagement here. And the best thing about convolutional neural networks and image analysis is just the ability to show pretty pictures. We're doing product classification. You can make a picture, but they're not like this. This is great. Cool. So I'll send out a link to the mask RNN, and then also the is that code open source or?
Yes, I will push it to GitHub.
Cool. So I'll send that out to the meetup group, and if you guys, as always, have speaker ideas, things that you guys want to hear about, just let me know, and we'll see if we can get it on the agenda. All right, thanks everyone again.